Hi viewers, welcome to all. Here we are discussing about a project design of SEU Tolerant 2D-FFT in SRAM-based FPGA. Okay, so here the project description says that 2D-FFT is called two-dimensional fast Fourier transforms has been widely employed in a processing of radar signal. The field programmable gate array is an excellent hardware solution for these applications due to the necessity for high performance. Okay, so here the single event upset, that is SEU tolerant in a static random access memory, okay, SRAMs, okay, based FPGA can produce a large number of soft errors in space-borne radar and synthetic aperture radar SAR. Okay, therefore the safeguarding the 2D-FFT implementations in FPGA against SEU is critical errors. Okay, in this paper we examine the significant weakness causes by SEU in the 2D-FFT process and then provide a 2D-FFT designs with a strong SEU resilience. Okay, this design takes advantages of many anti-SEU techniques. Okay, triple modular redundancy (TMR) is utilized in the FFT for butterfly control when reading and writing the data buffers with the error correcting codes. Furthermore, the critical storage registers to use a secure finite state machines and finding of fault injections revealed that the reinforcement approaches help to improve the capacity to attenuate SEU impacts. In the proposed approach, instead of RADIC 2, the proposed architectures builds the SEU tolerant 2D-FFT utilizing RADIC 4 design architecture to minimize the number of iterations in 2D-FFT to minimizing this logics with the garbage signals. Okay, so SEU tolerant 2D-FFT was designed utilizing the reversible array multiplier architecture. This proposed architectures was compared to conventional array multiplier architectures with the conventional full adders, and the performance of area, latency and power in Xilinx Vado ATIC 7 FPGA was demonstrated. Okay, now we can verify the base paper. So this base papers, they are designed the architectures. It's a 2D-FFT. So 2D-FFT is completely used for radar signal applications and also used for the image signal application. So this paper, they are focused for the 2D-FFT to reduce the error tolerant with the support of SAR. Okay, that is a synthetic aperture radar and a single event upset SEU. Okay, so based upon these two events, they plan to reduce the soft errors in the static random access memory based FPGA architectures. Okay, so here the applications part of this 2D-FFT algorithms, they are given with the image based processing with a high resolution technique of range Dopplers algorithms and chip scaling algorithms. Okay, so based upon this algorithm, the FFT architectures will be built with two level, that is a 2D-FFT. Okay, so here they are handled both FFT and IFFT architectures. As per the figure 1 architectures, they are given range Dopplers and chip scaling algorithm. Okay, so here you can differentiate the architectures in figure 1A and figure 1B. You can verify that. Okay, so left side it's showing a range Dopplers and the chip scaling algorithms. Okay, so this both algorithms we need to mix with and we are come up with a new architecture, that architecture given in figure 5. Okay, so it's a FFT and IFFT based architectures. Okay, so here the left side is a 1D-FFT and both left side and right side combined with that is called as a 2D-FFT. Okay, so this architectures we have built with the Verla HDL's code and synthesized in Xilinx ATIC 7 FPGA using Vado. Okay, and we have simulated within modelism software. Okay, and we are given a input signal in a sine wave pattern. Okay. Now we can verify the simulation and synthesis part. Okay, so before that we can verify the coding. Okay, so this is a Verla HDL coding for the existing model of conventional array multiplier based 2D-FFT architectures. Okay, so here initially start with numerical control oscillators. So here we have generated a sinusoidal modulation signal. So that modulation signals we have generated from here. So this modulation signal we are given in two ways. One is a real and imaginary. Okay, that part we are given into the top model architectures. Here top model architectures having a two architectures. So one is a FFT model, another one is a IFFT model. Okay, so here FFT model means this is the top model of the FFT architectures. It's having a splitter, okay, it's splitter, okay, and total factor ROM generations. Okay, so for coefficients memory, we have read the data from the total factor ROM, okay, and FFT IFFT core architectures, okay, and combiner. Okay, so in the IFFT architecture top model, it's having the transpositions block and total factor block, IFFT core, okay, and finally combined with the combiner. Okay, so after that we are taking the data in the simulation output. Okay, so here inside of this internal architectures, the transpositions and total factors ROM having a butterfly architectures with the radix 4 method. So here FFT IFFT core architecture, it's having a number of radix 4 in the final architecture. So here you can check it, radix 4 architecture of FFT. So here we are used number of radix 4 architectures, and some of the butterfly combinations we have used with the conventional array multipliers here, but in the proposed code we have used with the reversible array multiplier. So this is a reversible array multiplier component we are used here. So here we have used this paper for reference, high performance array multiplier using reversible logic structures. Okay, so here this reversible multiplier architectures was developed with the Feynman and Fredkin based half-adder architecture. So this is a half-adder architecture for Feynman and Fredkin gate. Okay, so based upon this architecture we have developed a 16x16 reversible array multiplier architectures with the 256 partial product generations and the added tree reductions method. Okay, so here the architecture of this reversible array multiplier, okay, it will be given in figure 3. Okay, so this architecture we have built with the reversible array multiplier. Okay, so after this process we can check this code in simulation. This is a conventional array multiplier based 2D-FFT architectures. Okay, so this code we have run up to 0 microseconds to 50 microseconds we have run it. Okay, so as per that you can check the data. So this is a data input real and data input imaginary, and this is a FFT output. Okay, and this is a IFFT output. Okay, so here you can check it. Okay, okay, so if we run with more time, so we will get a high and low based modulations also. Okay, and this is a proposed reversible method. So this code we have run with the 10 microseconds. Okay, so here you can check it. So if you need more time of executions, we can run it. Okay, so here you can check the input data and output data. So how much resolutions we will get in the final FFT and IFFT method. Okay, and this code we have synthesized in Vado, okay, with support of Arctic 7 FPGA. Okay, so here you can check the post synthesis and post implementation graph versus table. Okay, so this is a table for post implementation. Okay, and you can check the power analysis. So this is the existing part. Okay, and you can check the proposed part also. So here you can check the proposed part. This is a proposed post implementation method. So post implementations compared to existing and proposed, it's totally reduced. Okay, so here the post implementations, it will take 47% of LUTs. Okay, but using the reversible array multipliers we will get the proposed in 2% only. Okay, with the same FPGA, and the power consumptions and flip-flops also reduced. Okay, so here you can check the RTL schematic for this design. So here you can verify the RTL schematic. Okay, so here initially start with the data real and imaginary. It will be given into the FFT architecture. Okay, so this is the FFT architecture. Okay, so if you come back, you can check the IFFT architecture. Okay, so this is a transposition, IFFT, FFT core and combiner and total factor ROM. Okay, so in the FFT architecture, so splitter, IFFT, FFT core, combiner and total factor ROM. So in the FFT architectures, so here this is a proposed architectures. So here we have used as a number of reversible array multipliers and ripple borrow subtractors. Okay, and radix 4 architecture. So here radix 4 architectures we have used. So this is a radix 4 method. Okay, so here you can check the radix 4 FFT architectures. So this is a radix 4 completely. Okay, so it will be designed with the reversible array multiply architectures. Okay, so with the RCA, so RCA means here we have used with the full adder. So full adder, Fredkin and Feynman method. So instead of this full adder Fredkin, we have used a 2 half adder based architectures. Okay, 2 half adder means it will be designed with the Feynman gate and Fredkin gate. So this is a reversible architecture for Feynman gate and Fredkin gate. Okay. Okay, so this is radix FFT. Okay, so this is a FFT code. Okay, you can also analyze this codes in RTL view, and this comparisons we have updated in the comparisons document. Okay, so here you can check the comparisons of SEU Tolerant 2D-FFT in SRAM-based FPGA. So here we have compared with the conventional array multipliers and reversible array multipliers based FFT architectures with the 2D method. Okay, so here you can check the comparisons analysis chart. Okay, and finally the abstract document we have developed it. Okay, so this is a title and base purpose step, improvement of the project, proposed title, existing system, proposed abstract, okay, and related notes. Finally, literature survey and references. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.